Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to outline what this section is about. At this point, you know the two most important functions of a neural network, how to predict and how to train. So what else is there to do? Well, I've told you that neural networks are nonlinear classifiers, which means they can classify things when you can't draw a line between the two classes. Two classic examples for neural networks are the XOR problem and the donut problem. Recall that we already talked about these in my logistic regression class, the prerequisite to this course. In that class, I showed you that it's not possible to use logistic regression to solve those problems unless you manually create new features. In general, this is a time-consuming and tedious process. In this class, I'm going to show you that when you use neural networks, creating new features by hand isn't necessary because a neural network can, in some sense, do that automatically. But these advantages don't come for free. What you may have noticed is that neural networks come with a lot more options, like what nonlinear activation function to use, how many hidden units to use, and how many hidden layers to use. Choosing these isn't trivial, so in this section we're going to discuss practical tips for how to choose them. This section is all about applying what you've already learned about neural networks to gain deeper insight into how they work and what kind of baggage they come with. Hey guys, so this lecture is for those of you who did not take my logistic regression class and you want to review the donut problem and the XOR problem. Both of these problems are binary classification problems that don't have a linear boundary, but we were still able to use a linear classifier to solve them. The XOR problem is about learning the XOR logic gate. 0 XOR 0 and 1 XOR 1 is 0, and 0 XOR 1 and 1 XOR 0 is 1. You can see from this image that there is no line that separates the two classes. The donut problem is where we have two donuts with different radiuses. The boundary is a circle, which is obviously not a line. You will see in this course that we can solve both of these problems using neural networks. If you want to learn how we solve these problems without using neural networks, then check out my course on logistic regression, udemy.com/data science logistic regression in Python. It is also useful if you need to review log likelihood and gradient descent. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we're going to revisit the XOR and donut problems. We first saw these in my logistic regression class. So this is a little bit simpler than the neural networks we've been working with, since this is only a binary classification problem. The relevant file for this lecture is xordonut.py. So what I'm going to do in this lecture is I'm just going to walk you through the code rather than type it all out and run it, since a lot of it is repeated from before. First is the forward function. Since this is only binary classification, we're basically just doing two sigmoids in a row. And the predict function is no longer argmax, it's just round. The derivatives are mostly the same. And we're now doing binary cross entropy. Alright, so this is code that represents the XOR data. So 0 XOR 0 is 0, 1 XOR 1 is 0, and then 0 XOR 1 and 1 XOR 0 is 1. We're going to create a neural network with 4 hidden units. We're going to keep track of the log likelihoods. The learning rate is 0.0005 and the regularization is 0. So you could determine parameters like that by trying different values randomly or using a method like cross-validation. And so all this gradient descent code is pretty much the same as before. Notice how it now includes regularization. We do have some extra code here. So if the error rate is not equal to the last error rate, we're going to print the error rate print the true values, the targets, and we're going to print the prediction. So every time something changes, we're going to print out that change. We are also going to exit early if the log likelihood increases. Finally, when all that's done, we're going to print the final classification rate. Now let's look at test donut. So this is the donut problem. It's one class within another class. Okay, for this problem, we're going to have number of hidden units equal to 8. We're going to set our learning rate to 0.00005, and our regularization will be 0.2. And the rest of this stuff is exactly the same. So you see how with different problems, the neural network and the way that it is trained stays exactly the same. So you can plug and play with different data. You just have to intelligently choose the learning rate, regularization, and other hyperparameters. So let's run this for the XOR first and see what happens. Okay, so you see we can get 100% accuracy quite fast. Now let's try the donut problem. Feel free to fast forward through this part of the video if you are not as entertained by this as I am. Alright, so it converges quite quickly, and we end up with about 99% accuracy. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to look at another application of neural networks, and that's neural networks for regression. Most of this course focuses on classification for a few reasons. Number 1, classification is the typical use case for neural networks. All of the most famous results that have come from neural network research have all been on classification problems, going all the way back to the MNIST dataset and more recently the ImageNet dataset. All of these are classification problems, so that's why this course also mainly looks at classification. Number 2, neural networks are typically better at classification than regression. Now there are a lot of deep theoretical reasons for why that might be, but the technical issues underlying those reasons are beyond the scope of this course, so we won't be discussing them. However, as we'll show in the coming example, neural networks are still a fine choice for regression problems, and in fact, in certain scenarios, the advantages of neural networks may overcome the weaknesses. Neural networks for regression are actually used in some state-of-the-art applications, such as deep reinforcement learning. Number 3, the equations underlying the multi-class classification scenario are difficult to understand. You may have noticed that taking the softmax derivative was quite a bit harder than the sigmoid derivative, and it requires being very careful about indices and so forth. That's why I created 2 new lectures in the appendix to help students who are having trouble with this derivation. So multi-class classification is hard. That's why we spend most of this course on it. Let's go over again the structure of a neural network for regression by comparing it to classification. And let's, just for fun, consider neural networks with many hidden layers, since this is all conceptual and we won't be deriving any more equations. So for binary classification, what we have is a stack of nonlinear hidden layers, followed by a logistic regression at the end. And remember, I can call this logistic regression because this takes on the exact form of logistic regression, that is a linear transformation and a sigmoid. For the hidden layers, I don't really want to call these logistic regressions anymore, since they still do linear transformations, but the activation function is not necessarily a sigmoid. Still, the concept of stacking layers of neurons is important to consider, because that's what led us to these new structures in the first place. For multi-class classification, we have almost the same thing, just that the output layer has more units, one corresponding to each class. But notice how everything up to the last layer is the same as before. We have stacks of linear transformations along with nonlinear activation functions. Then at the end we have a multi-class logistic regression, which is a linear transformation and a softmax. Finally, we have the regression scenario. Again, notice how everything up to the last layer is the same as before. We have stacks of linear transformations along with nonlinear activation functions. At the end, we have only a linear transformation, and this is of course exactly linear regression. So what's the lesson here? We know from our previous studies that if we consider just linear models, we have logistic regression for classification and linear regression for regression. In a sense, we can consider everything up to the last layer just a feature extraction or feature transformation. We're transforming the input data into something different. And after that, we're just doing what we already know: logistic regression for classification and linear regression for regression. Now, since you've already seen the update equations for a one hidden layer neural network for regression, we're not going to repeat them here. What I'm going to do is show you the data set we're going to use, and then we'll look at the code to fit to this data set. Just like many of our other examples, what's very important about this example is that you can see it. So it's nice to consider 100-dimensional data sets, but of course you can't picture those because you can't see in 100 dimensions. So for this example, we're doing regression on a curve that you can see, which is important. Now you can see here that this data set is a saddle shape. The equation for this is pretty simple. It's just y equals x1 times x2, where x1 is the first input feature and x2 is the second input feature. So if you want to try to code this yourself, and you've understood all the code we've written up until this point in the course, then you are certainly ready. So if you want to pause this video and try it on your own, please do so now. So now we are going to look at the code for doing regression with a neural network. The relevant file in the course repo is regression.py. At the top here, you'll see that we are importing NumPy matplotlib and a module that's part of matplotlib called Axis3D. Now, some people, including myself, have had trouble using this on a Mac with Python 2.7. So if you can't get it working, then try using a Linux machine to run this, or try installing Python 3 in your system, which you can do using Homebrew. So let's copy and paste this into the IPython window. Next, we're going to generate and plot the data. So we create 500 uniformly spaced points between -2 and +2 on a two-dimensional grid. Then we multiply the first column of x's, which represents the first feature, by the second column of x's, which represents the second feature, to get y. Next, we do a 3D scatter plot of the data so we can see what it looks like. So let's paste that in. Okay, so here's our saddle. Next, we're going to make a neural network to fit to this data set. So first we define D, which is the dimensionality of the inputs, as 2. I've chosen the number of hidden units M to be 100, but you can choose anything you want. And then we randomly initialize the weights for the hidden layer and the output layer. So let's paste this in. Next, we have a function to calculate the output. So remember, because we're doing regression and not classification, we don't need a softmax at the end. And don't forget, we also need to return z, which is an intermediate value, because it's used in the gradient calculation. So let's paste this. Next, we have some functions to calculate the derivatives and do the gradient descent update. You've already seen these, so I'm not going to bother looking at them in depth. After this, we have a function to calculate the cost, which is the mean squared error. You can also do the sum. It doesn't really matter. So let's paste this all in. And next we have a loop that does the updates and keeps track of the costs. And then we plot the costs. So let's paste all that. Okay, so we see that the cost has converged. Next, we want to plot the function that the neural network has learned and compare it against the data. So to do that, we first repeat the code we saw before to make the scatter plot. And then after that, I'm going to create 20 evenly spaced points on the x1, x2 plane in both directions. To do that, I need a function called meshGrid, which basically gives me back every x1, x2 coordinate in that box. If you want to see exactly what meshGrid returns, you can try printing it out. But just to give you the short version, what we need to do is flatten those two arrays and then stack them beside each other to get an n by d matrix that I can pass into the neural network. So I do that and I get a new y hat. Then I can use this trisurf function to make a surface plot of all my new y hats. So let's paste this in. So we can see that the neural network has learned this function pretty well. So you can try rotating it a little bit. But we can also see that it's a little bit off in the corners. And it kind of looks like the closer we get to the corner, the worse the prediction is. So it's hard to see the middle because there are too many points in the way. So let's close this and go back to the code. So one idea is we can just plot the magnitude of the residuals at each point on the x1, x2 grid. So let's try that. Okay, now I don't really know what these colors mean, but I can guess that the corners are the worst predictions. So the light color means that it's bad and the darker color means that it's good. So you can see it's not uniform around this grid. So let's go back to the code. So let's try to do another 3D plot of these residuals just to see what it looks like. Okay, so this confirms that the corners are the worst, but there are also other pockets where the error sort of gradually increases and decreases, right? These pockets here in the middle. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we're going to look at various nonlinearities that you can use in your hidden layers and their derivatives. Choosing which one to use is like choosing hyperparameters. You should try a few and pick the one that works best. The first we'll talk about is one you've already seen, the sigmoid. If you don't already know how to take its derivative, I would recommend doing it as an exercise. The next function I'll talk about is the hyperbolic tangent, which we've also seen. As an exercise, I would recommend trying to find the derivative of this, and also showing how tan h is related to the sigmoid mathematically. You should find that tan h is just a sigmoid that is scaled both horizontally and vertically. The last nonlinearity we'll look at is the ReLU, or rectifier linear unit. This one is a bit weird because it actually looks kind of linear, and it is in fact linear in the two regions. Despite how simple it looks, it performs very well, and I almost always use the ReLU as a default. because the derivative is always 0 or 1, it is also computationally efficient. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to talk about some practical considerations for activation functions for the hidden layers of a neural network. The main ones we've looked at in this course were the sigmoid, tanh, and rel-u. And so just to be sure, we are not talking about the activation function at the output, which is always going to be the same depending on what task you're doing. So that's the sigmoid for binary classification, softmax for multi-class classification, and identity for regression. So this lecture is dealing with hidden layers only. So this lecture is meant to answer the question of which one should I choose? A lot of people, when they start machine learning, are intimidated by the huge number of options. There are just too many decisions to make. So it's nice to have some hard and fast rules to follow. My main advice is always to experiment first and get a feel for how things work with your dataset. But there are also some universal truths that might help you guide your decision, so that's what this lecture is about. So let's start by talking about the sigmoid. The sigmoid, as you saw in our earlier studies in logistic regression, is of theoretical interest because it goes between 0 and 1. This is a lot like the biological neuron because they operate on the all or nothing principle. In other words, the neuron is firing an action potential or it's not. It also makes the neuron completely uniform. Every neuron is the same, just like the brain. So you have this repeating structure, which is the same thing over and over again. And the idea that if somehow when you put a bunch of these things together, that they'll do something intelligent is a very satisfying idea. But in reality, neural networks are more about function approximation than modeling the brain. Modeling the brain is more in the realm of computational neuroscience. It's not about making good predictions on data. And that's what we're here for, to make good predictions on data. So one problem with the sigmoid is that most of it is flat. Flat means the derivative is 0. So why is that a problem? Well, if you think about it, how does a neural network learn? We know that neural networks learn using gradient descent, and the gradient is the derivative. So if the gradient is 0, then the neural network is not going to learn. So we have this problem where unless the data is in this very small region, it's going to learn very slowly. Note that the slope is never actually 0, but very quickly approaches 0. And then if you get far enough, it's just going to round off to 0 due to the limits of numerical precision. But there is another problem with the sigmoid. Recall that we like to normalize our data before putting it into machine learning algorithms. That means mean 0 and variance 1. Having the data in a small range helps us with the previous problem of where if the inputs get too large, the derivative goes to 0. But what happens when the input to sigmoid is 0? Well, we actually get 0.5. So the sigmoid basically keeps offsetting the data. Even if your input is perfectly standardized to have 0 mean, after it goes through the sigmoid, it's going to be at 0.5. So then we have the tanh. The tanh, as you can see, solves the problem we just talked about. When you put 0 through the tanh, you get 0. However, the ends of the tanh are still flat, so we still have the problem of slow training when the data is off to the edges. In general, the tanh is typically better than sigmoid, so if you have to choose between these two, you probably want to go with tanh, unless there's a specific reason you want to stick with sigmoid. You'll see at least one example of that in a future course. Neural network researchers were very stuck on this S-shaped curve for a long time. It's clearly nonlinear, and we need nonlinearities in order to create a nonlinear function approximator. But nowadays, we have the rel-u. The rel-u is kind of an ugly function, and maybe that's why neural network researchers were stuck on the S shape for so long. For one, it contains a max, which looks really strange. And it looks kind of like a broken stick, which is not smooth, and so, because of that, the derivative is not defined as 0. That might bother someone who is too theoretically inclined. However, in practice, the chances of the input being exactly zero are infinitesimally small, so assigning the derivative either way doesn't really make a difference. For example, you could say the slope is 1 if x is greater than 0, or you can say the slope is 1 if x is greater than or equal to 0, and it wouldn't really matter. So how does the ReLU perform relative to the tanh and sigmoid? Well, you may have noticed that it trains a lot more easily. In this course, we look at the TensorFlow playground, which allows us to see the decision boundary that is found by the neural network as it learns. You see that the ReLUs have these really jagged decision boundaries, which in a way sort of suggests that they let the neural network contort itself more easily into different shapes. The ReLU also trains faster. Now you might think, well, the ReLU is still flat in 1/2, and unlike the sigmoid and tanh, the derivative here is exactly 0. So there's this whole region of space where the neural network cannot learn. But there's still a whole region of space on the right side where the ReLU is steep. In fact, the area where the ReLU derivative is 0 is a known problem in deep learning. It leads to what are called dead neurons. Essentially what happens is the activations go down to 0, and because the derivative is 0, the weights behind it don't get updated ever again. And so those neurons are always just computing zeros. So we call them dead neurons. One solution to the dead neuron problem is just to add more hidden units and hope that not too many of them go down to 0. Generally this is fine and we can outperform the tanh and sigmoid. Another option is to use what is called the leaky ReLU. This is where we give a small positive slope to the left half of the ReLU. So it still looks like a broken stick, but the left side derivative is no longer 0. This solves the dead neuron problem, but interestingly, it could actually make your neural network perform worse. Now that doesn't mean leaky ReLUs are worse, that just means hyperparameters are synergistic. In order to get the best result, you have to choose the right learning rate, the right architecture, the right activation function, and so on. For some problems, for certain settings of hyperparameters, I've seen the sigmoid work best. So that's just something to remember. Just because everybody is using ReLU now, doesn't mean it's the best all the time. You still have to experiment and test different settings so you can find what works best for your particular dataset. However, it is true that today most people just use the regular ReLU by default due to its relatively good performance. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. You may have noticed that throughout this course, certain steps seem sort of arbitrary. Like, why do I choose the learning rate I do? Why do I use 4 hidden units and not 5 or 10 or 1000? What's the difference between choosing the tanh activation function and the ReLU activation function? All of these are great questions. These are called hyperparameters, meaning they are parameters that we have to choose that are not part of the model itself. So how do you choose the correct hyperparameters? Well, I would first like to start by saying that there is no precise way to do this. I know this makes a lot of you uncomfortable. How can this be science if there's no exact answer to something? Well, you could obviously write your own program to test every single possible value, but you can imagine how that might be prohibitively slow, in fact, just infeasible. A lot of people ask me, how can I get more practice? And they don't realize practice is right in front of your very eyes. In order to be good at deep learning, you must have experience. That means working on different problems and manually finding the best learning rate for that problem. All problems are different, and the learning rate will be dependent upon your neural network architecture, the size of your network, the size of the data, the structure of the data, and so on. We've used learning rates from 10 to the minus 1 to 10 to the minus 7, which is 1 million times smaller. If you don't know what kind of data to use for practice, just ask yourself, what would I be interested in predicting using data? There are many examples throughout this course, and if you work for a corporation, hopefully you know enough about the business in order to apply machine learning in a meaningful way. So that's number 1, practice makes perfect. You want to find something you're interested in and apply your knowledge. If you get stuck, ask questions. Next, let's talk about cross-validation. This is a very simple process, but just in case you don't know, the idea is this. All data is signal and noise. You want to train your model so that it learns the signal and not the noise. If you make your accuracy too high, you might get perfect accuracy, which means you fit to both the signal and the noise. Here's a visualization of what fitting well and overfitting might look like. So on the left we have a good fit, and on the right we have overfitting. This is why we split into train and test sets. We want to follow the error on both the data we're training on and the data we're not training on. If you start overfitting, you'll notice the test error increasing. To get a statistical measure of this, we want to measure it several times and take the mean and the variance. That's what cross-validation is for. The idea is you split your data into k parts. Say k equals 5. We're going to do 5 iterations in a loop. On the first iteration, we'll train on parts 2 to 5 and test on part 1. On the second iteration, we'll train on parts 1, 3, 4, and 5 and test on part 2. On the third iteration, we'll train on parts 1, 2, 4, and 5 and test on part 3. We keep doing this until we go up to k. Once we're done, we can use the average classification rate as our measure of how good this particular configuration is. You can also use statistical tests like the t-test to compare two models to determine if one is statistically better than the other. This is just a function in SciPy. You don't strictly need to do this, but you may want to if you're statistically inclined. This course was not meant to teach you statistics, so if you're interested in that, you'd want to take a statistics class. So this is what cross-validation might look like in code if you wanted to try implementing it yourself. Hey guys, welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to discuss some practical methods for choosing the learning rate and regularization hyperparameters. This is a question I get very often because I think it makes people uncomfortable that there's some number you can't calculate, but that you need to find the answer to your problem. It's weird because this is science, and science is supposed to give you concrete and exact answers to things, and yet here's a thing that you need to choose intuitively. So the first step is to get over this discomfort. It will get more comfortable the more data sets you work with, and the more experience you get working independently. Let's discuss learning rate first. All I've told you so far is that it needs to be a small number, and you've seen some examples. The important thing here is the scale on which you try different numbers. For example, if you tried 0.1, then you don't really need to try 0.09, 0.08, 0.07, etc. It's better to go down on a log scale or by factors of 10. For example, if 10 to the minus 1 is too high, then try 10 to the minus 2. If that's too high, try 10 to the minus 3, and so on. At times, I've had to use a learning rate as small as 10 to the minus 7. Second thing here is, how do you know if your learning rate is too high or too low? It's easy to tell if your learning rate is too high. You'll see your cost blast off to infinity, or you'll get not a number output. The funny thing is your neural network will continue to train as normal, multiplying not a numbers as if they were actual numbers. So you need to stop your code manually. On the other hand, if your error or cost is converging too slowly, then your learning rate is probably too low. Try taking it up by a factor of 10 so that it learns faster. A good technique to use if things aren't working right is just to turn everything off, except for regular gradient descent. That means no regularization or anything else. Then keep lowering your learning rate to see if things improve. A learning rate that's too high might mess things up, but a learning rate that's too low won't. It will just train more slowly. If things still don't improve at that point, then there might be a problem with your code. In Deep Learning Part 2, we discuss how to train a neural network in batches of training data. When the data you're training on varies in size, the learning rate becomes sensitive to it. That's because the cost function is the sum of all the individual errors. So if you have a lot of data points, then the cost function will be larger. To normalize this, we just divide by the cost n, the number of training samples you're using at the time. That way, the learning rate can be chosen independently of the batch size. Similar to making the learning rate independent of the number of data points, we can also make the regularization penalty independent of the number of parameters. Just divide the sum of squares of all the parameters by the number of parameters. Note that I don't always do these normalizations, but it can be helpful to try if things don't work right away. One interesting obstacle I've encountered before is that I forgot to multiply my regularization penalty by the regularization parameter. That effectively made the regularization parameter a 1. For the particular problem I was working on, this regularization parameter was much too high, so my error rate just hovered around the point of random guessing. So sometimes it's useful to just turn regularization off completely and make your learning rate very small to see if your model actually works or if there's an error in your code. In this lecture, we are going to answer a common question I get, which is, why do we divide by the square root of input dimensionality when we initialize the model parameters? So, as you may or may not know, poor weight initializations can lead to poor convergence of your loss per iteration. Sometimes your loss might even explode to infinity. If you've never encountered this, then it's likely you just haven't practiced enough. Once you've seen enough datasets and done enough machine learning work, you will encounter a scenario where weight initialization matters. That's not to say it always matters, and that's not to say there won't be some instances where these recommendations will appear to perform poorly. My only goal in this lecture is to pass on some knowledge to you so that you know why it's usually a good idea to divide by the square root of input dimensionality and what exactly it accomplishes. Well, now that you know why we do it, let's talk about how it works. Let's start with looking at this initialization code. What does this do? Well, we know that the rand_n function draws samples from the standard normal, and that's usually denoted as n01. What happens if we multiply these samples by some number c? Well, you can show that if you multiply random samples from the standard normal by a number c, they will have mean 0 and standard deviation c. In other words, it's equivalent to sampling from the distribution n0 c squared. In fact, this is just the opposite of standardization or normalization. When we want to standardize a set of samples, we subtract their mean and divide by their standard deviation sigma. This makes it so that the standardized samples have mean 0 and standard deviation 1. Thus, we can perform the inverse operation as well. If we multiply by a number sigma and add a number mu on a standardized sample, the result will be a sample that has mean mu and standard deviation sigma. Okay, so now let's go back to our initialization. If we divide by the square root of d, this is equivalent to multiplying by 1 over the square root of d. Therefore, we're saying we want the initial weight vector w to have mean 0 and variance 1 over d. Alright, so why would we want to do that? Well, if we just start from some basic high-level principles, recall as I said earlier that if you don't do this, then your loss per iteration might explode. Well, the reason it's exploding is because those weights are too large, and if they are too large, that means their variance is too large, which means that we might be able to avoid this problem if we make the variance smaller. In fact, in some code, you'll see that people just multiply by a constant, like 0.01. This is also perfectly okay. Really, it comes down to doing experiments and finding the optimal value for your own data set. This is always the ultimate foolproof method. Okay, so we know that we want weights with small variance, but why exactly 1 over d variance? Let's go back to multiple linear regression, where we have d input features and 1 output. Since we have d input features, our weight vector will be a vector of size d. As you know, we like to normalize our data before passing it through any kind of model, whether that's a linear regression or a neural network. Again, it's all about experimentation, so if you've never seen this for yourself, then find some datasets and try it on your own. The onus is on you to gain experience. In any case, if we normalize our data, that means each input feature will have mean 0 and variance 1. Let's see what we can do with this. Suppose we want to know the variance of the output y. Why do we care about the variance of y? Well, you know that in neural networks, after the first layer, you simply have more layers of the same type. Therefore, the output of the first layer will be the input to the second layer, and so on. But since those will be inputs to the next layer, you want those to be normalized as well. If it's just linear regression, your target will probably be standardized, so there's still a reason to care about the variance of y. We know that the expression for y is just w1 times x1 plus w2 times x2 and so on. So how do we calculate the variance of y? In fact, since all the w's and x's are independent, this expression simplifies to what you see here. It's just the variance of w1 times the variance of x1 plus the variance of w2 times the variance of x2 and so on. Well, we know the variance of all the x's. That's just 1 because we've standardized our data. And we also know that the variance of all the w's will be the same. There's no reason to make the variance of each of the w's different. So we can just call them var w. And in that case, we get that the variance of y is equal to d times the variance of w. What does this lead us to conclude? In fact, it means that if we want the variance of y to be 1, which we do, then the variance of w must be 1 over d. This is the same as saying we want the standard deviation of w to be 1 over the square root of d. Finally, I want to make a note that this is not the only way to initialize weights, but the general theme remains that you want the variance of the weights to be initialized to small values. Other methods include the he-normal, the Glorot normal, and so forth. Typically, these are used in deep neural networks and not linear models like linear regression. Also, as mentioned, it's pretty normal to just multiply by a constant value like 0.01. But as usual, the best way to determine what works best for your dataset is to do experiments and see the results for yourself.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to summarize everything we did in this section of the course and talk about next steps. The previous 2 sections taught you all the important aspects of neural networks, in particular, how to do prediction and how to do training. These are, of course, essential parts of any supervised machine learning API. This section built on that by giving you more practice and perhaps answering some unanswered questions, like what are hyperparameters and how do you choose them. In particular, I wanted to stress the importance of being able to visualize what a neural network is doing by using 2-dimensional datasets, which are easy to understand visually because you can plot them on a 2D grid. We looked at the XOR problem and the donut problem specifically. You may recall that we also looked at the XOR and donut in my logistic regression class as well, which is the prerequisite to this course. The key point with this is that neither of these problems are linearly separable, so you can't draw a line between the 2 classes. What you can do if you want to solve these problems using logistic regression is manually create more features. This is a process we call feature engineering. As you may suspect, manually doing feature engineering is tedious hard work, so we would rather avoid this if possible. We saw that neural networks offer us a way around this problem by virtue of being nonlinear classifiers. In particular, neural networks allow us to classify data that requires something more complex than a line to separate them. And it does this automatically without the need to manually engineer features. This is a big advantage of neural networks. Now, of course, we don't get all these advantages for free. In particular, neural networks have a lot more hyperparameters than logistic regression. You need to choose the activation function, the learning rate, the number of hidden layers, the number of hidden units, and so on. There are a lot more options to choose from, and choosing them well is not straightforward. What it amounts to is experience, and intuition that can only be built by experience. In other words, you need to practice a lot to be good. So this is the end of what I would consider to be the main section of the course. Everything after this is extra practice. So what comes next? Everything we've been doing up till now has been in NumPy. This is really important because you want to work directly with the matrices and vectors that we looked at in the theory sections. And this is a really important theme of this course. Everything we did always started out with some theory and some math, and then afterwards we directly translated that into equivalent code. Oftentimes, it was just a matter of writing out the equations we learned in code. So it was a direct translation of the equation you saw on paper into the same equation in code. No special coding knowledge was needed. In the next section, we take things a step further. As you probably already know, Google has a very popular deep learning library called TensorFlow. TensorFlow is very useful because it allows us to build big, complex networks without increasing the complexity of our code. In particular, you may have noticed that the hardest part for us was writing backpropagation in code, since it involved multiple levels of matrix operations. In TensorFlow, you'll see that the library takes care of all that stuff for us. So TensorFlow is very beneficial in that regard. It takes the hard work out, since we no longer need to derive the update equations and implement them directly. At the same time, there isn't now a one-to-one correspondence between the theory and the code. So what that means is you'll need to familiarize yourself with the quirks of the TensorFlow API, which is not as straightforward as NumPy. TensorFlow has a great online tool for visualizing what a neural network has learned, called the TensorFlow Playground. So we are going to look at this too. As I've been saying throughout the course, it's really important to be able to visualize what a neural network is learning. So using this tool helps solidify that idea. After that, we go through some miscellaneous stuff, like how to get more practice with deep learning, how to make sure you really understand everything in this course, and so on. It'll also give you some ideas for what to study next in deep learning. Deep learning is a huge field. There are tons of different kinds of neural networks, and they are all at varying difficulty levels. So these lectures should give you some idea of what's out there and how you can apply the things you learned in this course. In the section after that, we have the Facial Expression Recognition project. This was designed to give you extra practice with the concepts from this course. In particular, you'll be using a facial expression dataset, and you'll be trying to categorize emotions. This project appears in multiple of my deep learning courses, and the purpose of that is to get you applying different architectures to the same dataset. In this way, you can compare and contrast the results you get. For example, one method might take longer to train, but achieve better accuracy. This is very common in research. We call these benchmarks. And we use benchmarks to compare algorithms. So this project is good to do if you want more practice. In this project, we build our models using classes, so you'll be able to apply your object-oriented programming skills. You'll see that this is cleaner and more organized than the procedural code from earlier in this course. The goal is to get it looking like the scikit-learn API, which is a popular machine learning library in Python.